In this video, we're going to start to take a look at some of the aspects of gases in particular, and look at how we can predict and talk about some of the properties of gases in relation to the forces that affect their behavior. In order to really discuss this, we have to talk about what we call kinetic molecular theory. Kinetic molecular theory has several components to it, but the very basics of it is that the particles of a gas are in constant random motion. And so think about the gas and the air in your room where you are right now. The oxygen, the nitrogen, the carbon dioxide, the water vapor, all the different gases that make up air are constantly all zipping around and moving around. Constant random motion. Some of the other aspects of kinetic molecular theory are that the volume of gas particles themselves are negligible. And so essentially we say that the gas particles have no volume, especially when compared to the space that they're in. The attractive forces between gas particles are negligible, basically meaning that the intermolecular forces that would normally hold them together are not present. And that's mostly because the particles have enough kinetic energy to overcome any of those intermolecular forces. They might still be there, but the energy that the particles have, the kinetic energy the particles have, is so much greater than the energy of those intermolecular forces. And the temperature of a gas depends on that average kinetic energy. So as we're discussing some of the various gas laws and properties of gases, we have to define pressure. That's one of the primary ways that we measure a gas, is by how much pressure it exerts. So remember that gases are also compressible. And so we can compress gases into a smaller size. That's essentially why, or not essentially, that is what allows scuba divers, for instance, to go down and use scuba tanks, because we can compress the air that they need, put it under a lot of pressure, and put that into a tank. The gas particles themselves, remember, gas particles are always in random motion. And so picture that scuba tank that's now filled with compressed air. That air is still all moving around. And so eventually that air is going to bump into the wall of the container. That's really what we consider to be pressure. And the measure of pressure is a force per unit area. And so we can see a good diagram of that here. So here's our container wall. And here we have our gas particles slamming into it and then bouncing back off. That creates what we think of as pressure. And that's one of the views that I want us to keep in mind as we talk about some of the various gas laws that we're going to be talking about. That pressure is really a measure of the gas particles colliding with the sides of the container that they're in. Several different units. You can hear my kitty here wanting a little attention. But several different units that we might use for pressure in general. One of the basic ones is called an atmosphere, or an ATM. One ATM is essentially equivalent to what the pressure would be, air pressure would be if you're in Portland. It's equal to the air pressure at sea level. And then a few different conversions that you might have to do. There's also just different units of pressure. Millimeters of mercury. 1 ATM is equal to 760 millimeters mercury. Torr is another pressure unit. And so 1 ATM is also equal to 760 torr. Pounds per square inch might be a pressure unit that you're familiar with. That's what we measure the pressure of tires in. And so that's pounds per square inch of the tire hitting the inside of the tire. The 1 ATM equals 14.70 psi. Pascals is another one that's sometimes used, a little bit more infrequently, but you might see that if you're looking at some other resources. And 1 ATM equals 101,325 pascals, or 101.325 kilopascals. Air. So air is a mixture. About 78% of air is nitrogen, about 21% is oxygen. Then there's also some trace amounts of water, carbon dioxide, and argon. A couple other little things, but those are the primary components. Atmospheric pressure, when we say the like air pressure, essentially, air pressure is equal to the force of air molecules pressing down on the earth. So you can think of it literally as all that air that's above you pushing down. And at sea level, like I said, atmospheric pressure is equal to 1 atm. Barometers are what we use to measure air pressure. And so in a barometer, and this is why one of the units of pressure is millimeters mercury. So this would be a diagram of an early barometer. We would have this little container of mercury here. As atmospheric pressure pushes down on it, we also have this tube, and some of the mercury is going to climb up that tube as the atmospheric pressure pushes down. And so the way that these work is literally we just measure how far up the mercury travels up the tube. 760 millimeters of travel is what we get when we have standard air pressure. So that's 760 millimeters mercury. Higher altitudes have less air pressure. That should just make sense. There's literally fewer molecules pressing down. And we end up with less oxygen per breath. And this is one of the reasons that airplanes have to be pressurized, because as you go up, there's a lot less pressure up there. We get up to 10,000 meters, we get up to the cruising altitude of a lot of airplanes. There's only about a quarter of the same pressure that there is at sea level. Same thing happens as you go down, by the way. If you're going down into the sea, you get more and more pressure due to the forces of water that are above you. So as you get down into some of the deep sea, you get about 2,000 meters down, about a little more than a mile down. Now we're experiencing pressures of over 200 atm at that point. Pretty high pressures. Oops. And so air pressure decreases as you get higher in altitude. When we think about a gas in general, when we think about the properties of a gas, the properties of a gas are described by four variables that are very related to each other. Pressure, which we've talked about, the volume of the container that the gas is in, the temperature, and the number of moles. What I like about these as we think about them is these relationships that we're about to discuss also just make sense. When you think about how changing one of these variables might change another one, it just makes sense when you think about it. And so changing one of these variables will affect the others in very predictable ways. The first we'll talk about is Boyle's law. And so if temperature and the amount of the gas remain constant, so we're not changing temperature and the amount, as volume decreases, pressure will increase. They're inversely proportional. Again, that makes sense. Think about it. If we have a balloon that's this big, it has a certain pressure in there. If we don't change the temperature, so the average kinetic energy is not changing, the speed of the particles isn't changing, the amount isn't changing. If we then expand the balloon to this big, we're going to have fewer collisions on the side of the container. So the pressure is going to decrease. So pressure and volume are inversely proportional. We won't go through much of the math of it, but that means that we can write them like this, which ultimately means that if we have an initial set of conditions, and this is how we'll use Boyle's law. If we have an initial set of conditions, then that pressure times that volume will equal a new pressure times a new volume. And so for instance, so let's look at actually, no, we'll keep it conceptual with this example, then we'll look at a mathematical example. So breathing. When you inhale, your diaphragm moves down. And so deep breath in, your diaphragm moves down. That increases the volume of your lungs. Therefore, the pressure decreases, and so air will flow in. Breathe out. Diaphragm moves back up, decreases the volume, increases the pressure in our lungs now, so air will flow back out. And we can see that illustrated here. Rib muscles contract, expanding your rib cage, diaphragm moves down, lungs increase in volume, decrease pressure, so air moves in, and vice versa. Breathe out, diaphragm moves up, lungs decrease in size, increase in pressure, air moves back out. Here's a fairly painful example that can happen sometimes: the bends. You might have heard about this with diving. What can happen, or what does happen, is if a diver starts going down deep into the water, due to another law, which I don't think we'll really talk about in here, but due to another gas law called Henry's law, gas particles are more soluble at higher pressures. And so what happens is when a diver dives, nitrogen moves from the high pressure area in the lungs into the blood, into the relatively lower pressure in the blood. And so nitrogen gas moves into the blood. If a diver then comes back up slowly, then that's fine. The nitrogen is going to leave the blood back into the lungs and everything's going to be fine. Diver comes back, oh, sorry, that was the too quickly. Here's the slow path. Diver comes back up too quickly. And what happens then is now we've got these nitrogen bubbles in the blood, come back up, pressure goes down as we come back up from the sea. So the pressure goes down. What happens to the volume? Volume of those nitrogen bubbles expands drastically. It's in your blood. You die. Potentially. If you come up too quickly, absolutely, you would die from that. And so that's a very real consequence of Boyle's law. If you come up too quickly, there's still too much nitrogen in your blood, that those nitrogen bubbles expand. And it's a very bad, very painful situation. Let's look at an example of where you might do a calculation with Boyle's law. So you might have maybe, let's say you've got a balloon that is, we'll say, I don't know, 4.5 liters. The pressure in that balloon is 2.5 atm. And then we somehow decrease the volume of the balloon. So we decrease the volume down to 2.5 liters. We want to know the new pressure. So we'll use our Boyle's law expression. I think in the slides I used P initial, V initial, same thing. P1 V1 equals P2 V2. So this first volume that we were given here, there's our V1. Here's our P1. That's our initial pressure and our initial volume. Our volume 2. And we're looking then for P2. So what I would do first is algebraically manipulate this equation. And so we're just going to do a little basic algebra to this and get our P2 equals P1 V1 all over V2. And then we can just plug those numbers in at that point. We know that our initial pressure of 2.5 atm, our initial volume of 4.5 liters, then all divided by our new volume of 2.5 liters. Oh, and I didn't even do this intentionally, but the way the math of that will work out is our new pressure is then going to be 4.5 atm. And we see that our pressure went up. That makes sense because our volume went down. So that's how we would use Boyle's law. Charles's law is now going to look at the relationship between volume and temperature. Now we have to note here that we have to use the Kelvin scale for temperature. If you want to go into the reasons for it, shoot me an email and we'll talk about that in further detail. But for our purposes, if you're comfortable just knowing that we have to use the Kelvin scale and this is how we convert, then that's enough from my opinion for this course, is just to know that we have to do this and this is how. We're just going to take our Celsius temperature and add 273. That gets us to our Kelvin temperature. And so Charles's law tells us that volume and temperature are directly proportional as long as pressure and amount stay constant. So again, that should make sense. If I have a balloon that's this big and it's got a certain temperature, if I increase that temperature, now my pressure has to stay the same. So I've increased the temperature. The speed of the particles is therefore going to increase. Since the speed of the particles is increasing, my collisions are going to increase unless I also make my container bigger. Making that container bigger is the only way to keep the number of collisions the same. And so if I increase the temperature, my volume will also increase. Mathematically, that comes out to VI or V1, but V1 over T1 equals V2 over T2. And we would do calculations with that in a similar fashion that I just demonstrated with Boyle's law. If you have an initial set of conditions and you're trying to find maybe a new volume, then you would just set up the mathematical expression, and go from there. But we can see this by heating a balloon. So this is exactly how hot air balloons work. I take a hot air balloon and it has a certain volume of air in there. That volume of air, or that amount of air rather, the amount of air isn't going to change. But I heat it up and that's going to increase the volume. Now the actual amount hasn't changed, but now the volume has changed. The volume has increased. That's going to then decrease the density until eventually the density of air inside the balloon is lower than the density of air outside the balloon, so it floats, and then it'll lift. We can use Charles's law to experimentally determine what we call absolute zero. So if we look at this example here, what we can do is we can take data of if we have some sort of container where we start to decrease the temperature, or we get essentially, we just get Charles's law data with our temperature on our x-axis and our volume on the y-axis. And we can get a certain amount of data, and this is what this is showing here. It's just some data that we're going to take, change the temperature, that'll change the volume, and we measure those. What we can then do is just extrapolate that line. So that'll give us, since it's a linear relationship that gives us a nice line, we can extrapolate that line down to the x-intercept, where where the temperature, where the volume would be theoretically equal to 0. At that temperature, that's what we call absolute zero. At negative 270 degrees C, that's the point where theoretically all molecular motion would stop. And so everything that we talked about with particles moving, that all stops. Any motion inside the atom, electron movement, all motion would stop. That's what is meant by absolute zero, is we can reach a point where all molecular motion stops. And we can predict that point by using Charles's law data. We also have Avogadro's law. Avogadro's law, again, is one that just makes sense. If the pressure and temperature remain constant, then the amount of gas is directly proportional to the volume. So again, I'm keeping my pressure and temperature constant. If I put more gas into this balloon, it's going to get bigger. And we could work with that mathematically just the same way that we would work with Boyle's or Charles. We can then put them together into what we call the combined gas law. We can take Boyle's and Charles and combine them together. This would enable us to do calculations where maybe we take a balloon and we have it at sea level and we bring it up to the top of a mountain. And so our pressure is going to change because air pressure is changing. Our temperature is going to change because it's getting cooler up there. And so we could predict the new volume of the balloon if 2 factors change. And we would do that with the combined gas law here. We also have the ideal gas law. And I'm just going to, I thought I had it written out, but I don't. It's written in a weird way. Let me write the ideal gas law differently for us here. The ideal gas law, PV equals nRT, where P equals pressure, V equals volume. Pressure in this case must be in ATM, volume must be in liters, N equals our number of moles, R equals the ideal gas constant, which I'll talk about in a moment, and T equals our temp in Kelvin. So as a side note that I didn't mention before, in Charles's law and the combined gas law, your temp has to be in Kelvin. But for Charles, Boyle's, the combined laws, your pressure and your volume don't necessarily have to be in ATM or in liters, as long as it's consistent. And so in other words, if your P1 is in ATM, your P2 will be in ATM. If your P1 is in atmosphere, or is in millimeters mercury, your P2 will be in millimeters mercury. For the ideal gas law, however, you must use these units. R is the ideal gas constant, which is equal to this number here, 0.08206 liters ATM over mole Kelvin. Actually, I don't want to talk about that one. I will talk about this, though. So the question is, when do you use which one? When do you use Boyle's, Charles, or Avogadro, or the combined versus the ideal gas law? You would use Boyle's, Charles, Avogadro, or the combined gas law, whichever one's appropriate depending on the information you have. You would use those if you're comparing two different situations. In other words, for instance, if you have a balloon that has a volume of 4 liters at sea level, so we know that it's V1 equals 4 liters, P1 is 1 ATM, T1 is 23 degrees C, which would convert to Kelvin. And then we want to know the volume on top of Mount Katahdin. We have a new pressure, we have a new temperature. So we have one situation and we have a second situation, and we're comparing the two. That's when you would use either Boyle's, Charles, Avogadro's, again, or the combined, when you have those two different scenarios that you're comparing. The ideal gas law is more of a one snapshot in time. So we're not comparing two different situations. We're saying, for instance, how many moles of air are in a 4-liter balloon, which is at 1 ATM and 23 degrees C. So one moment in time, we would use the ideal gas law to find whatever information we were looking for. Dalton's law of partial pressures. All Dalton's law of partial pressures tells us is that if we have a mixture of gases, each of those exerts its own pressure. And so the oxygen in the room right now that I'm in exerts a pressure. The nitrogen in here exerts a pressure. The CO2 exerts a pressure. So each of those exert an independent pressure. But when we add those all up, that's going to equal the total pressure in the room. And so Dalton's law of partial pressures tells us that the total amount of pressure when you have a mixture of gases equals the sum of all of the pressures of the components. And that's really all there is to Dalton's law of partial pressures. Henry's law. So I said that I wasn't sure if we talk about it. We'll just mention it here. Is that Henry's law tells us that the number of gas molecules dissolved in a liquid is directly proportional to the pressure of the gases. In other words, you can dissolve more gas in liquids at higher pressures. It's particularly valuable in anesthesiology because that means that if we increase the pressure, we can get more of the gases into a patient. It's also something that you'll notice if you open up a carbonated beverage. Open a carbonated beverage and you get all the bubbles that rise up and that come out. That's because in the bottle or in the can, that carbonated beverage is under pressure. Once you open it up, that pressure decreases, and so a lot of that carbonation, a lot of that CO2 is going to escape because now your pressure is going down, so the gas molecules can't stay, the same number of gas molecules can't stay dissolved in there, so some of them escape immediately. And then our last slide just gives us a basic review of each of the laws. Boyle's law is the relationship between volume and pressure. Charles's law between volume and temperature. Avogadro's law between volume and amount. We have the ideal gas law, which combines all of them together. And then Dalton's law of partial pressures. And we're not going to do any calculations with Henry's law, so don't worry about that. Just know conceptually what it is. And that ends our discussion of gases. You stay classy, USM.